Alright, so in this video what I'm going to do is I'm going to talk about position and displacement vectors. We use position and displacement vectors quite extensively in physics to understand motion of a particle. So let us first draw what a particle, how a particle moves. So in order to do that, we define our coordinate axes, x and y, like so. And let us have a particle moving in, say, this direction, along this line, something like this. Let that be the trajectory of the body that's moving. And we want to understand what happens to this body at different time and how its physics changes and where the body emerges and what time, at the time at which the body is at a particular position, things like that. So we want to analyze the motion. So this here, because we have drawn it on a 2D plane, is called motion in a 2D plane or motion in a plane. All right. So in order to do that, we are going to use one construct in physics, which is known as position vector. So if I were to ask you to look at a particle and tell me what happens to the particle at different positions, different time, well, you're going to look at the particle and you're going to see where your eyes move, where your head moves, and you're going to track the particle by the motion of your eyes. And based on that, you're going to tell me, wait, at that point of time, the particle moved a certain amount of distance, and this is where the particle ended up finally, things like that. So in physics, the way we define eyes is to define a reference. And reference works wonderfully well if we choose it to be the origin. So this is the origin, and we define this to be the eyes of our 2D motion. With respect to this point, we're going to define vectors that work the same way as our sight did when we were tracking the position of a body. So let's consider 2 points at 2 different points of time. The first point here, say point A, and the second point there, point B, and we ask ourselves, how does the motion look like when we're looking at the body from the origin, and where did the body finally go? So in order to do that, we define 2 vectors, first one joining O and A, origin and the body at certain point of time. So let's say that the body was at A at time t, and the body was at B at time t plus delta t. That means if we track the motion of the body, it took delta t amount of time to go from A to B via this trajectory. So with that in mind, let us draw our vectors. So the first vector that I'm going to draw connects O and A in this manner. This is the position vector of the particle at time t, and we're going to refer to this as r of t. So this is the position vector, that's why you have r with a vector sign, and at a function of time, and this is at time t. Now when a clock strikes time t plus delta t, the particle is at B. So we're going to draw what the position vector looks like when it's at particle point B. So it's going to be the line joining O and B in this manner. This would be my vector, or rather the position vector at t plus delta t time. So this would be r of t plus delta t. Alright, so that is the position vectors. Those are the position vectors of particles at point A and point B. Now, with the position vectors now defined, we can define something which is called displacement, or rather displacement vectors. So displacement vectors actually is basically the difference in position vectors. So I'm going to call them as p dot v dot. And there's a very important reason why we work with displacement more often than position, because if you look at position vector defined with respect to an origin of our choosing. They have no binding whatsoever on the motion of the body. So I could have chosen my origin here, I could have also chosen my origin there, and I could have defined 2 vectors, this and that, defining the positions of position vectors of the body with respect to this origin. I could also have done that with this as the origin, or like I did with this at the origin. So it doesn't really, it's not a unique position about which I can define position vectors. However, once I know the position vectors, I can easily get rid of this bias that I introduced by defining an origin of my choosing. And I can do that by taking the difference of two position vectors. Now, if you look at this diagram here, if I define a displacement vector d as the difference in position vectors, this is the sign for delta, which is very often used as a difference. So the difference would therefore be r of t plus delta t minus r of t. Now, more often than usual in physics, we define the difference as a final quantity minus an initial quantity. So there you have it. That's one very fundamental rule in physics. Even in the case of kinetic energy or potential energy, you always have the difference to be final minus initial many times. All right. So the final vector, the final position vector is r t plus delta t. That's at the final moment, after which we stop considering the motion of the particle. This is the last point during which our clock actually ticks. After that, we're really not concerned what happened to the body. And the initial one is point A, where we started considering the motion. We started tracking the body. So if you look at the difference, and this is what we call the d, or the displacement vector, then that would be this vector. And there's one very easy way to really understand why this is the case is that if you consider what happens if you add r of t on both the sides, you get r of t plus delta t. So you're asking yourselves, wait, what vector I must add to r of t in order to get r of t plus delta t? So you can look at the image at this point and answer that question. So our final vector that we are seeking is a resultant of d and r of t. So that is r of t plus delta t. And we're asking ourselves, what must I add to r of t in order for it to give me r of t plus delta t? The only vector I must add to r of t is which emerges from the head of r of t and ends at the head of r of t plus delta t. In that manner, I'd be forming the familiar triangle and invoking the triangle rule to graphically represent this equation. Therefore, the displacement vector, when defined as final position vector minus an initial position vector, effectively becomes this vector. So that's a displacement vector. Now, if you go back to the bias that we introduced in position vectors with respect to the origin, we really disregard that now, because this displacement vector doesn't really have to do anything with where we defined our origin. If I had chosen this as my origin, I would have gotten two very different vectors. First position vector would have been this, and second position vector corresponding to B would have been that. But the difference still would have been this. So even when the position vectors are defined with respect to a different origin, the displacement vectors would exactly be the same. But the displacement vectors also would only depend on the initial and the final position of the body over the time period over which we're considering the motion. So the important point of displacement vectors is the fact that they have no binding on where we choose our origin, and also that they only depend on the initial and final position of the body, not on the motion of the body in terms of its trajectory. Because you can see that the displacement from as what we get from this definition is as though the body moved directly from point A to point B across the arrow. But that's clearly not what's happening. The body is moving along the white line all the while. It's only that at two different points, it seems as though the body moved from A to B. But that's not the case. Even if that's not the case, we can still define important concepts like velocity, displacement, and accelerations and things like that. So I'm going to do that with velocity in mind. So at this point, I have a displacement vector, and that is equal to r of t plus delta t minus r of t. This is my displacement vector. Now, in order to find an average velocity, what I can do is I can divide displacement by time. The time over which I'm considering the displacement, that's delta t. Now, you may ask yourselves, wait, d vector is a vector. This is a vector quantity, whereas delta t is a scalar. So it's as though multiplying a vector by a scalar, and that gives us another vector in the same direction as displacement vector. because delta t is positive. So that means our average velocity itself is a vector. So we can define average velocity as v vector, and that becomes equal to d vector divided by the time. I can expand this as follows and call this r of t plus delta t minus r of t divided by delta t. Now, if you look at this form of average velocity, which is the distance traveled, displacement traveled rather, divided by the time, this gives me average velocity. And it's very similar to how we define derivatives in mathematics for functions. We choose the values of the function at a certain position and subtract it from a different point at some other position and divide that by the difference in the x-coordinates, and that gives us the derivative of the function. So in that manner, this is how we define velocity, very similar to that. And this is how average velocity looks like. It's the displacement divided by the time. Now, if someone were to ask you, what is the distance traveled? Well, the distance traveled would be dependent on the trajectory path. That would be the length of this blue line that I'm drawing right now. And that would be something that would only be able to be acquired after we have studied the trajectory of the particle. We cannot know that just by looking at the displacement vector. And if we want to define the speed, the average speed, that would have been the distance divided by the time. So that would be delta t. And the distance is given by the blue line that I ended up drawing right there. This kind of like this shaped, this curvy blue line I've drawn there. So that's the total length of the blue line divided by the time. This gives me average speed. Now, if you notice, distance is a scalar, time is also a scalar, and a scalar divided by a scalar itself is a scalar. Hence, average speed is a scalar, but average velocity, just because it includes displacement, is not a scalar, it's in fact a vector. So that's how you define average velocities, average speeds, and many other concepts related to that. So I hope this video made sense. I hope it clarified why we need position vectors and displacement vectors in the first place to understand the motion of the body in 2D, or in fact even in 3D. You can do the same thing in a three-dimensional case and use those informations to evaluate things like average velocity, average speed, and acceleration. And that is something I'll go into further videos, but I hope this video made sense, and if it did, then all the best, all the very best.